Hello again, here we are. This time we're looking at a concept called resolvance. And resolvance is not to be confused with what we were doing with the single slit when you had two stars and you were doing the Rayleigh criteria to decide if two objects can be resolved. And unfortunately, this has a similar name. This one, resolvance, has a different equation. As you can see here, it has a different equation. But it's really about something else. It's about not resolving two objects, which is like called angular resolution. But instead, this is about being able to tell the difference between two spectrum lines for a chemistry emission line. So even to be able to understand what this question is about, you have to know some chemistry that IB in their wisdom thinks you learned in 10th grade. So I don't know if you know that chemistry, so I'm going to review that chemistry for you right now and then come back to resolvance. And that's the way we're going to attack this. Here we go. Let's see, I'll move that out of the way. And to understand this chemistry, we're gonna look at an atom. And this is like old school, you know, n equals 1, n equals 2, n equals 3. And this is looking at right there, if you can see, there's the electron, and there's only one electron. All these other things, I'll get this running, are actually just photons coming by. So these are photons of lots of different colors that happen to be going by this atom. And this atom only has one electron on it. And it's kind of small. It's this little guy right here. You can see it. They've made the photons really big so you can tell which colors they are. But the idea is, let's keep track of that little electron. There it is. There it is. Oh, no, there it is. Where's it going? Oh, what? Oh, no, didn't move yet. There it is. So, oh, where'd it go? Oh, there it is. So this electron here is jumping whenever photon gets absorbed by it. And I'll try to slow this down. Maybe we can see it happen. Maybe that's too slow. We won't. Oh, there, good. So the electron will drop back down to its ground state. And then if the right color hits it, but only the right color, if the right color hits it, it gets pushed up to another level because it absorbed the energy. See how the photon disappeared also? So here's an electron, and it gave away that photon. So when a photon is absorbed by an electron, it jumps up. And if it jumps back down, it gives away a photon. And the color that it gives depends on the amount of energy associated with these electrons changing different levels. And electrons have different levels because if you remember, there's like the 1s, 2s, 3s, or maybe way back to 8th grade where you said, oh, there's 2 in the first level, then there's 8 in the next level. Anyway, as the electrons change their energy, photons are absorbed or emitted. Now, what's happening down here, and I'm going to speed this up for a little while. We'll just throw a lot of photons at it really fast. Let me get that dial going. And here we're keeping track of which colors got absorbed. Okay, and when the color gets absorbed, we mark it down. And you'll notice only certain colors get absorbed. And this is back to learning about why there's colors. Like people say, well, why is your shirt yellow? Your shirt's yellow because it absorbs some colors, but it reflects yellow. And then we all say, oh, that's why it's yellow. But it's actually much more complicated than that. Things absorb. Okay, that's a little crazy. I'm going to slow that back down to more reasonable. Light goes fast, but just so we can get the idea. But you can see there's certain colors. So what happens, I'm going to stop this. What happens is that a given absorption where the electron goes up or down means that a specific color is absorbed or released. And every element has its own like distinctive sets of energies that it will have. Because if I change what element I have, the levels here are going to change. And the amount of energy that the photon that gets absorbed will be different. And these little lines where it's absorbing will be in slightly different places, slightly different colors. Okay? So that means that different elements have different spectrum. So let's look at a periodic table here real quick. And let's look at sulfur, for example, has these particular colors that get absorbed. If we look at nitrogen, it has these particular colors. Look, those two greens are right next to each other. I wish I could remember which one I just clicked. Was that, what was that? No. You'll know because you were watching the video. That one was a great example, but you can see how every single one has slightly different lines. And this one, see how these two green lines are almost on top of each other? Can you really tell there's two different green lines or not? These two yellow lines are a little easier to tell that there's two different lines. That's what resolvance is. That's what this whole lecture is about. Can I tell these two lines apart? Is this actually two lines? You just can't tell. This is two lines. I can tell them apart. I needed a certain diffraction grading in order to be able to tell that these two colors were separate colors. These greens, there's two of them, but can you really tell there's two of them? I don't know. How good are your eyes? In any case, the idea is different colors give you different relationships to atoms. Oh, nice. There's two more. This is another element that had the same two green lines. It had a similar jump there. So that's in one of the examples we're about to do. So how do we get those lines anyway? So a diffraction grating will take the light and separate it into its colors, because as you know, different colors will have different angles, because we already learned that. As you go through a grating, different colors will have different angles. So I did this in class here, because I'm at school for a minute. And I put this on my wife's Facebook just as a way to show the video that I just took. And I was looking at neon gas, and then I'm going to look at it through my camera through a diffraction grating. And the neon that looked orange only, we can now see that that orange light is actually made up of a whole bunch of different colors, right? There's a blue, there's yellows, there's these reds. And look, on the one side, this is -1. On this side, the +1, you can see the colors get divided. But if you look over to m equals 2, you can see the colors get separated even more. So the first one, the first order, has some separation, but the second order has even more separation of the colors. And so the more separation you get, the easier it is to tell those colors apart. Whew. So this only shows m equals 1, but m equals 2, which would be way over here, there'd be more separation between the blue and the red. So when we look at this, we can see the separation, and there's two yellow lines there. It's really hard to tell. Actually, no, there aren't two yellow. There's a yellow, and then there's this orange that's next to it. And they get sort of blurred together here at m equals 1. But m equals 2, you can start to see there's two different lines. So m is which order you're at. Are you at, this is m equals 0, never works. So at m equals 1, there's some separation. At m equals 2, there's even more separation. Okay, lambda is that particular color you're looking at, that particular yellow color, for example. That's lambda. And delta lambda is the difference between the two yellows when you look in really carefully, and you can see that there's actually two different yellows there, and that you can tell them apart. As we saw with this periodic table, these two green lines, delta lambda would be the difference between these. You know, maybe this is 551 and this is 552, then delta lambda would be just 1 nanometer, because that's 550 nanometers. And then for lambda, you just use the average of the two numbers, so it doesn't really matter that much. Okay, so that's what we're looking at. And so the chemistry that's important tells us that any particular jump of the electron gives us a very specific color. And every element has very specific colors that will get absorbed. Those are seen in this spectrum here, this atomic spectrum of what the electrons are doing. And each specific color has a particular wavelength associated with it. And if there happen to be two lines right next to each other, we wouldn't be able to tell them apart. Looks like there's two yellows right there in this mercury. Can we really tell them apart or not? Depends on how good of a diffraction grating you're using. Okay, specifically, how many lines will the laser beam hit? The lines could be really close to each other, so the laser beam will hit more of them. Or if it's a really big laser, the laser beam will hit more of them. So N is simply how many grating lines will be hit by the laser. M is the order, whether you're looking at the first order or the second order. Lambda is the wavelength of that particular line that you're trying to tell as two lines. And then delta lambda is the difference between those two lines when it looks like you actually, you know, might only have one line, but you realize there's two lines. Okay, some examples. Two quick examples. The first one is this one on the right. I want to talk about it. It's super important, and it's an interesting site if you go to this site. And this is a DDD that I'll do to do the actual math with it. But just so you get the idea, this is a spectral analysis of a chemical in water that they're suspected is polluted, and it might have some arsenic in it. And arsenic is this distinct line. This is an absorption line. And then this is the cadmium that isn't as dangerous for you. And they want to know how much arsenic there is. The problem is these two lines are right on top of each other. So how can you tell the difference between the arsenic and the cadmium? And the article I got this picture from is actually looking at using artificial intelligence to study the actual curves that you get when you look at these particular spectrum and deciding, because just looking at it, it's too difficult to tell, but maybe the AI, the artificial intelligence, can actually figure out if there is the amount of arsenic that you're after. Because look at these numbers, 228 nanometers, 0.812, 228 nanometers, 0.809, they're almost the same wavelength. So very hard to have resolvance on these two lines. If we looked at them, we'd just see one line there in the ultraviolet. This is in the ultraviolet, 228. In any case, that would be one example of two lines that you can't tell apart. Just as a quick side note, this type of spectrum is also how they look for at the airport when they swap molecules or atoms associated with explosives or drugs or whatever they're looking for as you get swabbed as you go through the airport. So that might have happened to you. This relates to that nicely. Another example that is one of my favorite is here's a spectrum of a star. And then when they looked at the spectrum over many days, like over a month, the spectrum does this like separation and then comes back together and separation and comes back together. But when you look at the star, you just see one star. But they realize that even though you can't have enough angular resolution to tell that there's two stars, by looking at the spectrum, you can see that there's two stars. This is called a spectroscopic binary in astronomy. And this line right here at 448.3 nanometers, this particular absorption line, separates and comes back together because the two stars are orbiting each other. And when one of the stars is coming towards you, right, it blue shifts a little bit. And when the other star is going away from you, it red shifts a little bit. And so this one line is really coming from two stars, but you can tell them apart when one star is coming towards you and against you. Where at day 1 or at day 11 or day 21, they're moving sort of in a circle sideways to you so you don't see them coming towards you or away from you. Where at day 6, day 16, and day 28, the stars are going towards and away from you as they orbit each other. So this is called spectroscopic binary because it's only the spectrum and this ability to resolve them that we use. So R is called resolvance. And the resolvance is given by R is given by the wavelength of that line. So you'd put 448.3 divided by delta lambda, which would be the difference between them. So in this example, lambda would be 228. Delta lambda would be 0.01 because this is 10 picometers, right? And that's not the same as in nanometers. Make sure these have the same units. And you can calculate what the resolvance is. And then what this here, the MN, is what order do you need, and then how many lines do you need when you use an actual diffraction grating to separate those lines, as we saw here when we did that. So I hope that helped us understand the idea of resolvance. There's a lot of information in a tiny bit of the curriculum. Mostly because there is a certain chemistry that they're expecting you to know. So there you go. I hope that helped, and now we'll do a DDD on it.